pleasure to have Franz Kristen here today. Let me give a brief introduction and then I'll leave the floor to him. So Franz Kristen is currently a postdoc researcher at Astron, the Netherlands. Franz earned his PhD at the Max Planck Institute for Radio Astronomy in Bonn in 2014. After that, he moved to Australia as a research associate at the Curtin Institute for Radio Astronomy in Perth. And then Franz returned to Europe in 2017 as a postdoc researcher at the Chalmers University of Technology in Gothenburg. There, he started the implementation and the coordination of a VLBI campaign to localize the repeating fast radio bursts using a network of European radio telescopes. He then moved to Astron. This was in the last August, so he's there and he's continuing his research on fast radio bursts there, and that's what he's going to talk today to us about. So thanks again, Franz, for being here, and the floor is all yours.
All right, thanks a lot for the intro, Marcello. Glad to be here. Thanks for the invitation. It's my pleasure to speak a little bit about fast radio bursts and what we do in our little collaboration to you today. So yeah, I'll speak about localizing and timing FRBs. So we're hunting these fast radio bursts, and of course, I do this on behalf of our precise team. I'll get to what that means in a minute. And all this is, of course, financed by the AstroFlash group, which is led by Jason Hestels at Astron. Now, just briefly on this Astron-Chalmers dualism. So since Marcello said I work at Astron, that is correct, but I actually do so from Gothenburg. So down near the Netherlands, Astron is somewhere here, and I'm actually up here close to Gothenburg because, that's one of those, I would call them positive outcomes of the pandemic, that everybody's realized, hey, we can actually work remote and it doesn't really matter where we are. And so I actually decided after the postdoc at Chalmers to actually stay here. And if you haven't been at Onsala, I encourage you to come because it's a lovely spot both in the winter and the summer. So Gothenburg is up here and we're actually, 40, 50 kilometers south by the sea. And there's a lot of geodesy happening with the twin telescopes that you see here. And of course, a lot of VLBI and astronomy with the 20 meter and the 25 meter. What you see here is the 25 meter dish. So 50 years old, but she's kicking and alive and doing great science. So fast radio bursts. Here's my take on fast radio burst and just in a nutshell, a broad overview. And after this slide, if you think you've heard all about FRBs, you can sort of fall asleep if you like. But so just in a nutshell, it's fast radio bursts are these millisecond duration bursts of energy in the radio band that are highly dispersed. Like I said, only the radio band. We have not seen them in the optical or gamma ray X-rays with one half exception, but so far only in the radio. It's a very common phenomenon. We see, or we expect to see, about 1,000 FRBs per sky per day, but obviously you cannot monitor the entire sky the entire day. The large dispersion measures, I get to what this is in a minute, but this dispersion measure tells us that these sources are actually extragalactic. And this in turn means, of course, that since they are at these huge distances and we see very bright signals, it means they are highly energetic outbursts of radiation. And to put it in context, so in about a millisecond, one of those bursts carries as much energy as the sun does in a day. So it's some sort of coherent emission mechanism, be it, radiation being beamed or in a magnetosphere or something similar. Now, we have about 650 published FRB sources. The vast majority have only ever been seen once. Those are the so-called one-off FRBs. And there's a small population of repeating sources, about 4%. And those are, of course, the most interesting ones for us at this point. And, right now, we still don't really know what is generating those bursts. Leading contenders are magnetars for the repeaters. And then, of course, this is the question of the one-offs are actually also potentially magnetars that just have not repeated yet, or if these are actually one-off cataclysmic events, this is still unclear. And if you're not an excited FRB astronomer or a pulsar astronomer, then why should you care about FRBs? Well, FRBs are actually excellent cosmological probes, and I'll touch on 2 examples of that in a minute. But let's start at the beginning. So the whole field was started in 2007 with the so-called Lorimer burst. Was Duncan Lorimer, who, together with a student, went through archival data looking for rapidly rotating astrophysical transients, and they detected what you see here with the Parkes telescope in Australia. And this is a plot of frequency on the Y, time on the X, and with the dashed line, you see the signal which goes through. And if corrected for this dispersion, you get this nice peak. Now, what is this dispersion? Dispersion is something we know very well from pulsars. Essentially, what you have here on the left is the same thing. So you have frequency going up and time increasing towards the right. And if you correct for this quadratic sweep in frequency, you get a nice burst that is inside here. And all this is just free floating electrons in space. And the frequency-dependent refractive index, as depicted here, causes a group delay, which then obviously causes the high frequencies to arrive for the lower ones. And the amount by which this is delayed, so how much delay there is in total, depends obviously on the number of electrons, and this number is what we call the dispersion measure. So it's the integral over the column density of electrons along a certain line of sight. Now for this Lorimer burst here, obviously when you have a model of the electron density, you can then infer a distance, and for the Lorimer burst, it inferred a distance of about a gigaparsec, so cosmological distance outside of our own galaxy. And at the time, people were extremely skeptical. Nobody had ever seen this. Why would there be such a burst? Question was, is this instrumental or is it not? Now, it took 6 years until 2013 for the next 4 FRBs to actually be found also in archival data and then be published by Dan Thornton. And also here you have these huge dispersion measures which imply distances of gigaparsec, 2-3 gigaparsec distances. So obviously redshifts of 0.23 whatever. Now obviously the way you can infer this is you look at the delay of this burst, and then you sort of realize. Okay, somebody needs to mute themselves. Anyway, so when you then do the numbers, you realize this total delay, only part of this delay can be caused by galactic electrons. So we obviously have a model of the electron density in the Milky Way itself, and then I realize, okay, only part of this can actually be caused by the Milky Way. All the rest must be from intergalactic space because the delay is too high. And then, you quickly realize, okay, this is something that traverses intergalactic space and then reaches us. Now, this is also where the first part of why FRBs are excellent cosmologic probes comes in. This is because the FRB sees each and every individual electron along the line of sight. And so these electrons are this very, very dilute and hot gas that is, not visible, which is this missing baryon problem that we can't account for all the baryons that we're expecting. This is something where FRBs actually come in great because, for each electron, there's obviously a proton if you think the whole universe is neutral on average. And so via the dispersion measure and because of this cosmologic origin, we can count each and every single electron and try and solve this missing baryon problem. Now, obviously, to be able to do this, you need to know an exact distance to these FRBs. We're inferring distances from models of electron densities, but of course, this is just a model. If we get our densities wrong, we get the distances wrong. So what you really need, you need to actually localize FRBs, and you need to pinpoint them to galaxies to measure a redshift to really get a distance, and then refine your electron density models. Now, but to do that, like I said, most of those FRBs have only ever been seen once. So if you really want to localize something, you need obviously something. You need something that is that repeats, because only then does it make sense to go back and try and find more bursts and localize, because typically you see them with single dishes. Now here in 2014, Laura Spittler et al. Found this very first repeater with the Arecibo dish, rest in peace. And now, since we had this repeater, of course, the obvious thing then is you just take your favorite interferometer and you stare at the field. You know, the localization from Arecibo was good enough, several arc minutes. You stare at the field, both, so one group used the VLA, another group around Benito Macoto et al., they used the EVN. And they were obviously, well, they were not really lucky because this is quite an active FRB, but both teams detected FRBs, or detected bursts from this particular source. Here's the VLA localization, localized to a dwarf galaxy at, you know, a redshift of 0.26, so at about a gigaparsec. And then with the EVN, with VLBI accuracy, they managed to actually localize the source to a star-forming region inside the dwarf galaxy. So here was the first hint towards what they could be, because, you know, it's localized in a star-forming region, and as later on was shown, it's also in an extreme magneto-ionic environment. So the rotation measure is massive for this source. That's a very turbulent environment, and the rotation measure gives you information about the magnetic fields. And so there was this first idea of that this could potentially, the engine driving these bursts could be the remnant of a superluminous supernova. So there could be some sort of, you know, a neutron star or a magnetar, or that is powering some nebula, and that is also causing the magnetic fields. But it could also still be some sort of intermediate mass black hole or something. Another thing that is, of course, interesting, why we come up with this idea of a nebula or an intermediate mass black hole or something of this sort, is that this particular FRB is associated with a persistent source. So there is a point source that is always on, that is very close to the source. Now, the repeaters actually also open up this next route where FRBs are potential good cosmological probes, namely if you have a repeater and assume you have a lens along the line of sight. So you have the FRB here, you have a lensing galaxy in between, and then any burst that arrives at us, at the observer, you know, it could actually go two ways, and then there would be a delay because the path lengths are slightly different, and you could actually detect the several bursts several times coming along different paths. And now if you go 5-10 years down the track, you keep monitoring the source, and then what you would expect, because of the expansion of the universe, you would actually expect to see a difference in the delays between the burst detected from one direction and the other. And Olaf Wognes actually showed that with this, you could also measure the Hubble parameter to quite high accuracy. Now, to do these sort of things, obviously, we need to find lots of FRBs, because by 2014, we had about 20 FRBs or so, mostly detected by Parkes. And since then, we have these two great FRB hunting machines. Here on the left, this is CHIME, the Canadian H1 monitoring experiment or mapping experiment. It's here close, not too far from Vancouver. It's a cylindrical array, huge field of view. And this is, at this point, the FRB hunting machine that we all use the most. And then obviously there's ASCAP in Western Australia. And the big advantage of ASCAP is what you see already. They detected, as far as I know, published about 50 FRBs. They probably have a lot more by now. But what they can do with ASCAP is they can do this so-called fly's-eye mode. So ASCAP is an interferometer, but you can use these dishes individually, so they can point in different directions, and then you actually map out a large part of the sky. So CHIME, like I said, it's got this massive field of view, 200 square degrees, and this is actually one of the main reasons why they were able to detect so many FRBs. Trouble is, their localization isn't great. It's typically tens of arc minutes. And as you know, within tens of arc minutes, you have several galaxies, and there's no way you can pinpoint it to any particular host. They are able, with so-called baseband recordings, to go down to tens of seconds, and this is great for us with the VLBI. We'll get to that shortly. But this sort of localization is not good enough to perform any sort of host assignments, let alone pinpoint them to an environment. In total, CHIME has published around 650 FRBs, 20 repeaters. And among these sources, among all these 650 FRBs, you can start to do statistics on the FRBs, and of course you find obviously a bunch of oddballs. So one of these is this particular source here, FRB 2018-0916b, R3 for short. And this particular thing has shown windows of enhanced activity, or actually it's only active during certain times. What you see on the top is a plot of time, so just normal time, and then the exposure time, and then you have in black is when CHIME was observing. The red markers and the numbers on top indicate how many bursts were detected in that particular period, and the gray shaded areas indicates a 2.5-day window with a 16.35-day periodicity. And as you can hopefully quite nicely see, is that these red markers all fall within this 2.5-day window. And this was also seen with the EVN and Effelsberg individually. And so here is some source that has an activity window that spans 16.3 days roughly. It's on for 3-4 days, and then it's off for a while, and that's actually it's been confirmed many times now. There is a hint for a similar periodic activity for this very first repeater, so the one that we localized first, R1 or 2012-1102A. And here's the similar thing. You have sort of the on windows, you have whenever something was detected, and then the white is the potential off window. And here we have a periodicity of about 157 days. Now there's the question, what is causing this? So first thing that comes to mind is obviously a binary system, that you have some object, and whenever the geometry of the system is right, you generate these bursts. Other ideas are that there is precession happening. For instance, in case of a magnetar, you have this beam of emission, and it precesses in one way or another. This particular source, it's not only that it has a 16.3-day periodicity, but it seems that there is a chromatic activity window. So here we have just the phase. So this is the 16.3 days, and then it's on for about 0.2, 0.3 of this on phase. Here we have the number of detections, and the interesting thing is that it seems that the bursts or that the source is active first at the higher frequency. So this is with aperitif at L-band 1.37 gigahertz. And then at CHIME, which observes between 400 to 800 megahertz, the bursts arrive somewhat later. And then at LOFAR, because this source is also in with LOFAR, it becomes active last. Around 150 megahertz. And so there the idea is that whatever there is, thanks to self-absorption or whatever in the early phases, the material is too dense, it's optically thick, but during the activity phase, it then becomes optically thin also to the low energy bursts, while the high energy has already moved out of sight. So this is sort of the idea behind this. The same source has also been localized by Benito Marcota et al. To this lovely spiral galaxy here, to the outskirts, and there is, there is this intriguing, triangular-shaped region of enhanced star formation. But the EVN localization is such that this particular source is actually slightly outside of this region of star formation. So it is associated with it, but it's too far. Even if you invoke high kick velocities for this particular source, it's too far away to be what many think is a young magnetar, because young magnetars, they're on for about, on the order of 10,000 years or so, but the distance between the region of star formation and the source is a bit too high for this to be a young magnetar. But also here, this millisecond localization is key to try and understand this source. Now, another oddball in the family of funny bursts is this one here on the left. So you have a very long FRB. So this is, this emission lasts on the order of 3 seconds. And if you look at it carefully, then you realize that these individual components, they have a very characteristic separation, and the CHIME FRB collaboration pinpointed this down to about 217 milliseconds with 9 components, but this is a complete outlier. There's a few others that show hints of periodic separation between the components, but it's nowhere near as significant. So this is apparently 6.5 sigma significance, but it's an outlier. So these are just a few of the oddballs. Now, when you do the statistics on the entire sample of the CHIME FRBs, there's 3 different plots here. So you always have duration of the burst, so the width of the burst, how long it lasts, and the bandwidth. And then this is separated for the one-off events and for the repeater bursts. And then what you see is that the one-offs, they typically span the full 400 megahertz of bandwidth that CHIME provides. So the one-offs, they're mostly broadband and they're quite short in duration, while the repeaters, they're somewhat narrow in bandwidth, so they don't span the entire 400 megahertz that CHIME provides, but they only appear in parts of the band, and they also appear to be longer in duration. Now that's just, a morphological thing. That's just what you see. It doesn't really tell you yet what is happening. So it could be due to beaming, it could be a propagation effect, it could be intrinsic. At this point, this is still unclear, but at least it gives you sort of a handle on if you have a burst that is a one-off event, rather narrow in bandwidth and longer in duration, it might be a good candidate to follow up because it could potentially be a repeating FRB that just hasn't repeated yet. Now, ASCAP, on the other hand, what is ASCAP? Because I said it's also a great hunting machine. They just detected a whole lot of bursts, but their great advantage is, of course, that there are an interferometer, and they don't just observe in this fly eyes mode, but also in interferometric mode. And thanks to the dishes being small, they still have a large field of view, so great chance to detect an FRB. And they managed to localize, I think, somewhere around 15 FRBs, give or take. But their localization is such that they can assign hosts, but they're not able to go down to the local environment within the galaxy. Nevertheless, great stuff can already be done because, of course, you can do population studies of what sort of hosts FRBs are emitted from. This is something that Shivani Bhandari has done, amongst others. And here, this is 2 plots showing, well, not quite the same thing, but hinting in the same direction. So you have the stellar mass against star formation rate. And down here is sort of the quiescent regions. And here we have the star forming galaxies. And, there is somewhat of a hint that potentially, FRBs could be rather associated with star formation than with quiescent galaxies. Similar idea here in the what is it, BPT plot? No, what's the name? BPT, I think. Where there is a bit of a hint that FRBs are either associated also with star-forming galaxies or with liners, but not so much with Seyferts. So, you may ask the question, so are FRBs actually related, associated with star formation? The localizations of the first repeater hints in that direction. The localization of R3, so this periodic source, it's close to a star forming region, but not in it. So that's a bit unclear. And there's been tests whether FRBs actually trace the star formation history of the universe, and it seems it doesn't really. If it traces it, then only with a delay of a few giga-years, and that is certainly too long for a young magnetar origin. So at this point, things are quite inconclusive. Now, another great thing that the late Jean-Pierre Macquart did is to actually take these ASCAP localizations with the host galaxies and their associated redshifts and look at the dispersion measure. And he then developed what is now known as the Marquardt relation, which links the electron density, or the number of electrons, to a certain redshift and cosmology. And here he's plotted the cosmic DM contribution against the redshift of a certain FRB. And as you can see, the FRBs that he used here follow that relation quite well. And in the same sense, he was then also able to put constraints on the baryon content of the universe. So this was the first attempt of actually solving this missing baryon problem in this way. Now, with all this information, can we actually, what actually are they? There are these bazillions of models. For the one-offs, it could still be cataclysmic events, say an evaporating black hole or supergiant pulses. Could they be related to gamma ray bursts at this point? Well, like I said, we haven't seen any counterparts. And the leading content at this point are still the magnetars. But what is it actually that we sort of need to really move forward in this field? And there, I'd say there's three different things. So one is the milliarcsecond localization of FRBs, because just knowing the host galaxy, it's great, but it's not quite good enough, because we don't know, is it star forming region, is it not, is it associated with whatever. So we really need this milliarcsecond localization to characterize the environment of those hosts. And of course, there is this question whether FRBs are associated with any type of persistent source. So is there a compact object that is always on or not? And this is only possible if we have this sort of milliarcsecond high sensitive localization. Two other important aspects are obviously what I've shown you on the right. This is this simultaneous broadband coverage, because despite many efforts, no FRB has yet been seen simultaneously at, say, P bands with 300 megahertz and L band and C band. So say 300, 1.4 gigahertz, and 5 gigahertz. To my knowledge, no FRB has been seen yet. It's always patchy. You either see it at 300, or you see it at 1.4, or you see it at C band. Haven't been that many of those, but there have been. So if we manage to get some broadband FRB, this obviously helps in determining what sort of emission mechanism could be at the core. And the other important part is, of course, the polarization. So the spectrotemporal polarimetry, which is, this where we're trying to figure out if the degree of linear polarization, which is here the red, or the degree of circular polarization, which is here in blue, if this can give us a clue on the emission mechanism or mostly on the environment. What's here on the top of these is always the polarization position angle swing, which for pulses has this characteristic S shape because we think it's a cone, and here it's typically flat, and this doesn't quite fit any pulsar magnetar model. And this sort of what we think can help us. Now, this is also where PRECISE kicks in, but because PRECISE tries to address these three questions. So PRECISE itself stands for pinpointing repeating chime sources with EVN dishes. So, we're obviously piggybacking on the chime repeaters, and we do this with the EVN dishes. And the EVN dishes that we use are pretty much all of the smaller dishes, because many of the smaller dishes, besides their VLBI, involvement, they often have a lot of time on their hand to do other science. And what you want to see FRBs is obviously a largish field of view, and most of all, you need a lot of time and patience to observe those. So PRECISE uses these smaller dishes here partially through regular proposals or letters of intent, director's discretion time. Now, since February this year, eMerlin is also part of our efforts. And this is great because eMerlin obviously provides the shorter baselines. And so for any FRB that we localize, if there is extended emission, without eMerlin, we would not be able to see it. But now that eMerlin is part of the array, it's not just that we have more baselines to play with, but we also have the intermediate length such that we're sensitive to extended emissions much more than what we are without. Now, the way we run this is that we also have the Effelsberg telescope and the SRT in our array whenever they can. At Effelsberg, we have 10 hours per week. And at Effelsberg, we record with both the DVB-C VLBI backend and the local pulsar backend. And at SRT, we implemented a similar mode with dual recording. So also there with the DVB-C VLBI backend, so recording baseband data, and with the pulsar backend. And until the currently running maintenance, we also had 6 hours per week. And of course, we're looking very much forward to the SRT coming online again to, have SRT in our array again, because it is the sensitive dishes in the array that help us actually detect more FRBs, because the chances of detecting FRBs are obviously higher the more sensitive your dish are. And the way we do this, we just cycle through the most interesting repeaters. And depending on what Chime sees, we can then obviously adjust our schedules. We're extremely flexible in terms of what we observe and when. And this is lovely. Data processing is such that we search both the baseband data is searched here at Onsala with a dedicated machine where we run both VLBI software and MVGI 5AB and regular standard pulsar software such as Digifill, using burst finders, Heimdall, and machine learning classifier as fetch. And we are at the point that we have turnaround times so from observations and then transferring the data and searching, we can be as fast as 24 hours. So within 24 hours of an observation, we know whether there was a burst or not. The pulsar backend data are not searched here at Onsala. They're actually searched at Astron, and they are searched through an independent pipeline that is Presto and Pulse Searcher based. And this is great because it's great that we have two independent data sets. One is affected in a different way than the other, and we have independent search pipelines making sure that that we can cross-check any candidates, and what's missed in one is hopefully not missed in the other, and vice versa. And of course, I don't do all this by myself. So here is 4 of the people that help: Mark, Omar, Kenzie, and Dante. Kenzie and Dante and Mark are already PhD students in the group. Omar is still master student and will be a PhD student in the near future. And of course, they help in a great deal and making all of this work. So the status of Precise in terms of how much we observe is, as you can see here. So on the X, you have the different dishes, and on the Y, there is just the total observing hours, color-coded by year. And on average, we've been observing around somewhere between 400 to 600 hours per year. At Effelsberg, like I said, we have these 10 hours per week. Of course, not every week, there's EVN sessions and whatnot. So in total, I think we get roughly about 350 hours per year on Effelsberg, plus about 240 on the SRT per year, which comes up to a nice 600 hours per year. And what's come out of it? What have we actually achieved? Well, we have already more than tripled the number of fast radio bursts with a milliarcsecond localization. So we have 2 already published, 3 are still to come, and from initially 2, that more than triples the number of FRBs with a milliarcsecond localization. And the 2 that are already done, so there is this one guy here, FRB 2020-1124A. This came out, or this was first announced in, I think, April or March last year by the Chime FRB collaboration. Many different teams jumped on the source because it was extremely active. And there were, ATELs coming out almost on a daily basis because somebody else had seen something. And then everybody also tried to localize it. And what you see here on the left is in the background is the dirty map of our EVN or precise localization, and then the rings, the circles are the different localization of different teams. So here, for instance, from ASCAP, this is the ASCAP localization. Then we have the UGMRT localization, and we have the VLA localization, the big circle. And then obviously here, our dirty map then pinpoints it down to milliarcseconds. And both VLA and UGMRT, and I think also ASCAP reported an extended source that is associated there, so a persistent source. But with the EVN resolution, we could actually not confirm this. Here on the right, you now see the same field as on the left, but integrated over the entire, I think, 10-hour run. So because on the left, we're only correlating the burst time. So this is just, well, we had 13 bursts detected. So this is combining 13 bursts of order 20 milliseconds of data. On the right, this is correlating, is a deep image, correlating the whole 10 hours of L-band data. And as you can see, there is absolutely no persistent source at the location of the FRB. However, the VLA saw this 22 gigahertz, this is by Peter et al., this 22 gigahertz extended emission, which we associate with star formation. So obviously this particular FRB is in a star forming region, somewhat offset from the core, but still this is a great example of potentially a young magnetar origin of an FRB.
10 minutes, Franz.
10 minutes. Gee, then I need to speed up. And the second great localization that we have is FRB 200120E, which is close to the M81 galaxy, which is right in our backyard, also announced last year. And Mohit Bhattacharya managed to localize it to this region here, where there's four potential counterparts. And we obviously followed up with precise, and what we managed to do is to localize the source to what turns out to be a globular cluster in this in M81. Now this FRB is not only the closest FRB at 3.6 megaparsec, but it is also the most surprising because this thing is now in a globular cluster where the others were in or close to star forming regions. A globular cluster, as you know, are extremely old systems where only old stars. So anything that could form a magnetar, any massive stars, would have burned out long ago. So here, if you invoke a magnetar origin, this particular FRB cannot be leftover of a recent supernova. There's no way. So we sort of invoke that it could be an accretion-induced collapse of a white dwarf or some other type of merger that generated, if it is a magnetar, that generated this magnetar, or it could be millisecond pulsar. But this is also one of those extreme outliers of localizations. But this is the value, the great value of milliarcsecond localizations. Now, a nice thing you can do with a source like this, because it has quite low DM and it's so close, you can start to try and constrain the dispersion or the DM contribution of the halo, which we here now limit to 35 parsec per cubic centimeter. These are nice trade-offs of these sort of studies. This particular source, since the properties are also interesting, here we have high time resolution profiles of the source with linear polarization in red and circular in blue, and the total profile in black. And also here we have flat polarization position angles and a large degree, close to, well, almost 100% in most cases of linear polarization. And then we have this one burst here that I'd like to draw your attention to. As you can see, it's resolved, but then there is this one peak that is not resolved. So, but since we always record baseband data, we can push the resolution to to the Nyquist limit. And if you do this, you actually realize that this is zoomed in on this peak. You realize that this peak is made up of many other small peaks on the 60 nanosecond level. And what this reminds us of is actually Crab giant pulses, because the Crab pulsar also emits giant pulses. And if you zoom in on these giant pulses, you realize they're also made up of these nanoshots. So if you put this in what we call the transient phase space, where you have transient duration on the x and luminosity on the y, you have the regular pulsars are down here, the FRBs are up here in the top, so they're all brighter. And then you have the Crab nanoshots are over here, so very, very short duration, very bright. And now if we put this particular FRB on the same plot, you see that the nanoshots, they're somewhat brighter, but very similar in brightness temperature to Crab nanoshots. And the pulses themselves are somewhere in between the regular FRB population and the pulsar population. So here we're starting to sort of fill the space between pulsars and FRBs with these sort of observations. Another thing we do with PRECISE is not just localization, but single dish monitoring of FRBs and similar sources, where we use these 3 dishes to sort of tackle this next idea of broadband detections of FRBs. So we use those 3 dishes, Westerbork, Onsala, and Torun, simultaneously at different bands to observe different sources, amongst others, obviously FRBs. And one thing we did was to actually follow up on this, galactic FRB. I'm always hesitant to call it an FRB because it doesn't quite fit the profile, but this was in April 2020 by now, that the CHIME collaboration detected this massive burst from the direction of this magnetar. And what's more, it wasn't only detected by CHIME, but also by STAT2, which is, this wild field, just a receiver on a stick, which sees the entire sky, not particularly sensitive. But since these bursts were so bright, both dishes picked it up. When I say bright, the CHIME burst is 700 kilojansky milliseconds, where the STAT2 burst is 1.5 megajansky milliseconds. So these are the brightest bursts we've ever seen from any such source. And if you were to put this source at cosmological distance, if it were to be at 70 megaparsec, you'd still see it with something like fast. So this could, for an extragalactic observer, this would have looked like an FRB. So that's why many people think this is potential FRB. And this also makes this link between FRBs and magnetars. Now, what's more is this one source even had an X-ray counterpart. So here, this is the radio burst in orange down here, the CHIME ones, and you have these 2 peaks plus another one in the X-rays. So this is this only example of a counterpart in different waveband. But even the closest, so the M81 repeater, even though it's the closest, if you look at the ratio, flux ratio between X-ray and radio, we would never be able to see any X-ray emission from the M81 repeater, just because the X-ray dishes are not sensitive enough. So since this was such a bright burst, we followed up on this source with Torun, Onsala, and Westerbork. What you see here on the top is just timeline and when which dish observed. So it's color coded which frequency band was observed as a function of time. And lo and behold, in about a month of daily monitoring, we found these 2 bursts separated by 1.4 seconds. And here, these bursts are 110 and 25 Jansky milliseconds. So comparing this to these kilojansky bursts, this is, of course, 7 orders of magnitude below, which is extremely interesting because obviously this particular source, SGR 1935 plus 2154, again, now bridges the gap between FRBs and pulsars in the vertical direction, where we did sort of the horizontal connection with the M81 repeater. Here we do the vertical connection, so similar duration, but spanning with one source, spanning 7 orders of magnitude. And down here, there's actually a detection also with the FAST telescope, which was on the millijansky millisecond level. So, as I hope I convinced you that with PRECISE, we're filling the gaps in this luminosity duration phase space, but obviously there's still a huge parameter space to be explored. So you say extremely long extremely long FRBs on the second level or extremely short. So I showed you this one example of an FRB that is composed of nanosecond shots. But what if there are actually, microsecond bursts? So this is a parameter that's not yet been explored. And as always, to do this, we need more observations, more data. And to do great science, you don't necessarily need the large dishes. It is actually possible with the smaller ones, but all you need is tons and tons of time. Yeah, we're still at the stage that the more we see, the more questions we have, even though we're moving in a certain direction, but it's still a great playground to look in. And that's all I had to say today.
Okay, thank you, Franz. That's great. Great talk, great timing. And so we have time for questions or comments and discussion from the audience. You people may raise their hands or write in the chat window. Okay, there's not much so far, so
all crystal clear.
Sorry?
All crystal clear or totally confusing?
No, I think it was very, very clear. And I guess the obvious question now, as also the things that you said are so clear, is about the future. So what are the the expectations for the coming years in the short term and even the longer term with the SKA, for example? And then we'll have a question by Maura and one by Cristiana. So
yeah, I mean, near future. I mean, of course, we're expecting that the next CHIME catalog to come out soonish as well, and there's going to be hopefully more repeaters in that we can follow up on. So I'm actually totally just expecting a lot more surprises in the near future with our localizations. And what we'd like to do, of course, is ramp up monitoring of FRBs with the smaller dishes. So, as you know, including some more of the European VLBI dishes, and then distribute the load of monitoring FRBs across different teams, where you then, cycle through all the repeaters, because, the repeaters that we haven't seen, we don't know. Many of those have bright bursts. We've detected other FRBs with the 25-meter dishes, and they potentially all produce these bright bursts. What are the brightest bursts? What's happening there? And a space we haven't really looked into yet is, of course, somewhere in the higher frequencies. The lower frequencies, LOFAR, CHIME, and so on, they have a huge field of view, but of course they're limited by scattering. Now you want to go up. So one interesting way to go is, of course, go to 5 gigahertz, something with a huge field of view, and then search that sort of frequency range, and then what you see there.
Okay. Yeah, I think that's really, really interesting, and I'm sure there are many people in this audience that that share this and have an interest in this and are happy to move forward along that way. So, Maura, do you want to add something more specific on this topic?
Yes, hi. Thanks, Franz, for the nice talk. So my question was similar, but more in detail on the future of PRECISE. I mean, you mentioned that, but how do you see the continuation of having so much time in the small dishes? I mean, people are starting thinking that they are useful, and then they will also want to use them. Or anyway, there's a lot of data involved in processing. So do you think it can be kept up for long, or at some point it will become very difficult? And another thing, it's just a curiosity, you mentioned that you don't call the burst from SGR 1935 an FRB. Is this just because it's galactic, or some other characteristics, I guess?
Yeah. Okay, let me do the second one first. So one thing is, of course, that it doesn't quite show those characteristics, right? So what we colloquially call the sad trombone effect. So that sort of, the components arrive first at the higher frequency, and then you have this meep, meep, meep sort of characteristic. This, I don't think we've seen this in SGR 1935 at all. So it's, if anything, the chime burst looks more like a happy trombone effect that's going up. So I think this is a bit confusing. And then it's quite broadband as far as we can tell. So the bursts we detected with Westerbork, they were completely broadband. There was no chunky bits in this range. And the last thing is, even though it was crazy bright, it's still, you know, effect of 30 fainter than the faintest FRB. You know, this gap is now closed with the M81 repeater, but since this is so close, none of the farther ones were as faint as the SGR burst. So, you know, yeah, that's sort of the reasoning in which direction that is going. And regarding the future of Precise, so I mean, at this point, running Precise, you know, we're sort of submitting somewhere between 5 and 10. I think I counted yesterday. I think it was 6 or 7 different proposals to different entities. One being the EVN for correlation, and then of course ENA for the Italian dishes, and eMerlin, and then the other dishes, and directors discretion time, and so on. So at some point, it would be very nice to actually have something that one might call an EVN light, such that this goes through the EVN, that the EVN, you know, offers more time on all the dishes, and that there is proposals that are, you know, Precise-like, but that can of course also do other stuff, such that you get some, I don't know, 1,000 hours per year on the smaller dishes, and people can apply. And then this is sort of with the smaller arrays, where not everybody is involved, where you want bright sources. So this would be nice if it went into that direction. And of course, other teams are going to realize, hey, the small dishes are useful for something, and which is great. You know, we don't need all the time. Of course, we want to have all the time. But if we broaden the science, it's great for everybody, if, you know, in terms of funding agencies and whatnot. But yeah, we'd like to move away from this ad hoc, in a way, road EVN operations and go to a more official way, which has pros and cons, but I think on the long term, that's the way to go.
Thanks, Franz.
Yeah, thanks. I see Christiana lowered her hand. Is that intentional?
No, it's unintentional. The question is still there. So
okay,
it's just a curiosity. You mentioned that you can use FRBs for tracing the dark matter halo of the Milky Way. So how do you exactly do that?
Okay, that's probably, it was probably not entirely clear. So we're tracing the DM contribution of the halo, because, you know, since the FRB is extragalactic, and for something like the M81 system, it is so close that the contribution from intergalactic space is of order one DM unit, so neglectable. Then, since it's in a globular cluster, you don't expect any gas to be there. So there, the contribution from the host is probably minimal as well. And given the look direction and pulsars in the vicinity, we know more or less how much the Milky Way itself contributes, and then whatever is left in the total dispersion measure that we see is most likely contribution from the halo itself. So that yeah, this is sort of how we probe the baryons in the halo in that direction.
Okay, thanks. No, so I was wondering just if you could use the globular, let's say the FRBs in globular clusters to trace the halo also in terms of dark content, but that's a different
that's a different story.
Yeah. And
I mean,
I have also another small curiosity, and that's about the machine learning that you use for finding the FRBs. So how do you train I mean, I guess it's difficult to train the machine learning algorithm on that.
So this particular package we're using, I have to say, I didn't write this myself, so it's a package we just used from somebody else. And this was trained on simulated FRBs. So the vast majority at the time when they wrote it, there weren't all that many around. And so this was trained on simulated data. And it comes with different models. I think there is 8 or 9 different models in that package. And we sort of just tested the different models on the different FRBs we have and on RFI, and then picked one that worked best for us. So yeah, it's mostly simulated data. I mean, by now, with something like this hyperactive repeater, where you have thousands of bursts, and also the very first repeater, there's also thousands of bursts, you could also retrain this network on real data, but then you risk biasing yourself to a particular type of FRB because they're all the same dispersion measure. And the 650 bursts from CHIME are probably not large enough a sample to train a reliable model. So at this point, you're limited to simulating things. But it works surprisingly well.
Yeah, that sounds a great result. Yeah, thanks a lot.
Yep.
Good. It looks like Sandro also has a question. We're close to the hour, but I think we can take it. Maybe try to keep it short question and short answer, please.
Sure.
Okay, thank you, Franz, and congratulations for a very nice talk and exciting results. The question is actually very simple. Could you please tell us something more on the gravitational lensing of FRBs? Elaborating.
Yes.
Before.
Yes, sure.
Mm-hmm.
So I think maybe I should just quickly go back to the plot, because that I think is the easiest way. I might have gone through this a bit too quickly. I realize that. Here we go. So say you have that FRB over here, right? And there is a mass concentration in the middle, and then you have the burst is going to be lensed or into your line of sight on either side of the lens, right? So if you were to image this, you would have sort of, multiple images on the sky. That's if you were to image it. But if we time it, because, this path length is shorter compared to that path length, you will receive the same FRB, but with a certain delay, just because of the different light travel time. And you will recognize it's the same FRB because, it will have the same dispersion measure. It will have the same characteristics, probably not quite, because it sees a slightly different amount of electrons on the way. But if you assume you can actually characterize it's the same because it's delayed by, I don't know, half a second or less or whatever, then okay, this is a lensed FRB that we see coming from two different paths. Now, if it's a repeating FRB, then you just keep monitoring this thing, and you measure the difference of the delay. So say, in year 0, you measure a difference of 5 milliseconds between the burst that comes along two different paths. Say 10 years later, you measure it again, and that delay has now increased from 5 to 10 milliseconds. And this is then the signature of the Hubble expansion, that your distances are becoming larger, and they become larger differently along the different paths. That's my understanding of how this is supposed to work. Does it make sense?
Yes, thank you. I was wondering whether would it be possible that the periodic microstructure that we see are also due to something similar, or they are too short in delays?
Ooh.
We have to work out the numbers probably.
Well, the thing is, there's too many bursts that show this microstructure that they should all be lensed. And as far as I know, along those different sight lines and those the localized ones that we have, and they typically all the repeaters are multi-component ones. I'm not aware of any galaxies along the way there. So I don't think that this multi-component structure is due to lensing. And
but could be something in the host.
You mean the multi-structure is something in the host?
Yeah. That would cause a very small time delay.
Oof, there I'd have to do. Yeah, we'd have to do the numbers there. Good question.
The path length would be similar.
Yeah.
So the delay should be short. Well,
yeah.
That's just a crazy idea.
Yeah. I mean, I think it's something we would have to do the numbers to see if that makes sense. I don't know from the top of my head. It's an interesting thought.
Okay, thank you.
Okay, we'll keep this in mind if anything comes out in the future that it was discussed past the hour of this very nice talk. So thanks again, Franz, for the wonderful talk and all the great work. Thanks everyone for attending, and that's it. Enjoy your lunch and talk soon. Ciao,
Thanks.
ciao, ciao.
Bye.
Bye-bye. Bye-bye.
Bye-bye.